Anyway, we'll just be looking at another method for solving ODEs. Okay, so good afternoon, everybody. So thank you for your patience for waiting for me today. So ngayon, pag-usapan natin yung isa pang klase ng methods para sa pag-solve ng ordinary differential equations. Because you remember last time we were talking about Taylor's method, which is supposedly an improvement from Euler's method. Ang problema natin with Taylor's method, napataas natin yung order ng accuracy. So from Euler's method, which is big O of h, we have reduced the error to order big O of h squared gamit yung T2 o yung Taylor's method of order 2. And we even pushed it to big O of h to the fourth using a degree for Taylor's method. So we were happy at first that we have developed a nice way of solving these equations. Kaya lang ang problema, napakamatrabaho. Ang laki nung kailangan nating computational expense na idagdag in order to get that high level of accuracy. Though we have seen that in our examples last time, nakita natin na worth it naman. Kasi even if we keep the same number of operations to be expended on performing the Taylor's method of order 2 or Taylor's method of order 4, look like in figure 11.5, where we only, when we restricted our methods so that only 40 function evaluations will be considered. So napakaganda pa rin nung result ni Taylor's method, which is actually about 2 orders of magnitude lower than that of Euler's method. So it seems it's worth it to do the additional computations kasi ang laki nung nakukuha nating improvements sa accuracy. But there's a catch. The number of operations there na binilang natin, or actually hindi number of operations, number of function evaluations. But those functions that needs to be evaluated dun sa higher order Taylor's method ay mga total derivatives. And if you have a very complicated right-hand side for your differential equation, remember we have a function f dun sa ating right-hand side, which is a function of the independent variable t and the dependent variable x. Kailangan natin kunin yung total derivatives. And taking the total derivative or computing the symbolic expression for the total derivative easily becomes cumbersome and very complicated, even for smaller values of n. Sinuwerte tayo yung example ko last time, ang ganda ng total derivative of order 2, 3, and 4. However, for more complicated functions, that might be very tedious. And medyo madaya nga, ang binilang natin ay number of function evaluations. So, ibig sabihin, hindi natin na-factor in kung gaano kakomplikado yung pag-evaluate ng bawat isang function. All right? And that's what we will try to address today. Can we find higher order methods na hindi gagamit ng total derivatives? Tanggap natin na kailangan natin ng additional computations in order to get better accuracy, but we don't want to use total derivatives. As much as we want that the additional computations would be evaluation of the function f itself. Hindi na tayo mag-introduce ng additional function, right? And that's what we'll try to do today. We will look at one class of such methods. Ang tawag natin doon ay Runge-Kutta methods, okay? So, paano nga ba mag-annotate dito? Okay, tingnan ko kung magagawa ko rito. So, itong Runge-Kutta methods, yun yung promise niya. Makakuha tayo ng higher order methods, okay? Pero hindi tayo gagamit ng total derivatives. But the nice thing about the Runge-Kutta methods ay magbabase siya dun sa Taylor's method, dun sa mga Taylor methods of a particular order. So the idea is we will look at Taylor's method, kaya lang i-approximate natin yung higher order terms o yung mga terms na nag-i-involve ng total derivatives by simply function evaluations. Okay? The derivations can easily become very cumbersome pag mataas na masyado yung order ng Runge-Kutta. Pero bibigyan ko kayo ng idea kung paano na-derive yung pinakamababang order ng Runge-Kutta method. Okay? And that's what we'll do today. So if we consider the same IVP na kinoconsider natin kaya lang dito nagpalit ako ng variable. Late ko na-realize. So yung independent variable x, nasulat ko siya as independent variable y in this section. So, but that's the only change and it's quite superficial. Okay. Remember that this is the second order Taylor method. So, oops, how do I do that again? Okay. So, sorry, nangangapa ako. Hindi ako sanay sa Adobe. Okay, there you go. Okay, yan. Oops, gawin nating... okay, so ito yung second order. Pero ayaw niya magsulat. Why? Ayaw gumana ng pen ko. But hopefully, but I don't know if you can see this. Nakikita niyo ba yung cursor ko? O hindi? But I'm looking at equation 11.9. Okay, kita. Sorry, hindi ako makapagsulat. Ayun, there you go. Kaya lang, nasaruduhan ko naman siya. Okay, so look at 11.9. This is basically the Taylor method of order 2, right? And again, order 2 yan. So kailangan natin ng first order total derivative ni f. What's happening? Anyway, so you see that term. Ang gusto natin ngayon ay makahanap ng paraan para hindi gamitin yung df over dt na yan o yung total derivative ni f with respect to the variable t. So that's our goal, all right? Find an approximation, hopefully of order big of h squared then para dito sa dyan sa total derivative na yan. Okay? So in order to do so, ang gagawin ko ay ganito yung template natin. Ang gusto kong mangyari, makahanap ng method na ganito yung itsura. Okay? So kung yung problem ay masusulat ko in terms of 11.7, okay, equation 11.7, tapos si phi, ang hula ko kay phi ay ito yung itsura niya. Okay. Ito yung right-hand side na gagamitin natin dun sa iteration. Because if I can write our problem in the form of 11.7 and 11.8, so kung susulat ko siya in terms of 11.7, I can just multiply both sides by h, and then add w sub I to the resulting side of the equations, we'll get a way to compute w sub I plus 1. Okay? Kaya lang, ang gusto ko si phi, dapat ganito lang yung itsura niya. Dapat siya ay a1 times function value of f plus a2 times some function value of f. Medyo dadagdagan ko lang yung time step dito by some constant alpha sub 2. Tapos, instead na y, yung ilalagay ko rito, yung second variable, dadagdagan ko siya ng konting increment. And that increment will be delta 2 times f of ty. All right. So the goal now is to find a1, a2, alpha 2, and delta 2 so that our phi in example 11.8 will approximate the right-hand side of Taylor's method of order 2. Right? So yung goal natin, makahanap ng a1, a2, alpha 2, at saka delta 2 para itong si phi ay good approximation dito sa kanan ng 11.9. Alright? And in order for us to do so, kailangan natin yung generalization ng Taylor's theorem para sa functions of more than one variable. So for now, we'll just be considering the smallest extension. Titingnan natin yung extension niya to order to two variables. And that's what is written in theorem 11.1. So here we are assuming that the function little f and all of its first and second partial derivatives are continuous on the rectangular domain D. So siya lang yung open interval AB cross open interval CD. And then we consider a particular point on this domain D. Tapos ang sinasabi ng, basically, pwede mo itong tawagin na Taylor's theorem, sa kahit anong delta T and delta Y, such that T plus delta T comma y plus delta y ay naroon pa rin kay D, may nag-exist na number C at saka number C between T and T plus delta T and a number eta between y and y plus lambda y such that the function f evaluated at T plus delta T comma y plus lambda plus delta y can be written in terms of this complicated summation here, right? So makikita nyo parang katulad lang to ng Taylor's expansion, right? So sa one-dimensional Taylor's theorem, meron tayo rito function value. Dapat yung pangalawang term doon ay h times derivative of f, right? Pero two variables tayo. So ibig sabihin, meron kang h o step size para dun sa variable t, tapos meron kang step size para sa variable y. Kasi instead of just an f prime dun sa one-dimensional Taylor's theorem, kailangan natin yung partial ni f with respect to the first variable and the partial of y with respect to the second variable. So yan yung first order term dun sa two-dimensional Taylor's theorem. Tapos remember, susunod dapat doon, h squared over 2 factorial, tapos second derivative ni f. So one-dimensional Taylor. Okay. So two-dimensional Taylor, hindi lamang isang klase ng second derivative yung kaya nating makompute. Meron tayong second partial derivative with respect to t twice. Alright, so ito yung partial with respect to t, tapos ipa-partial mo ulit with respect to t. So may kaakibat siya na multiplier na h squared, which is the step size in t all over 2 factorial. And then here we have the second partial derivative with respect to t and with respect to y, evaluated at the unknown elements of d na si c at saka si eta, times the product of the respective step sizes with respect to each variable. And then, ganun din sa dulo. So, ito yung lahat ng posibleng second order terms, sila yung nag-represent ng error. Okay? So, this will give us a nice way of approximating the right-hand side of the Taylor's method of order 2 in the same format that we wanted. Kailangan ko lang i-match itong expansion na ito. Alright? So, basically, dito manggagaling yung Runge Kutta of order 2. So, paano natin siya ma-derive? Well, gagamitin ko gagamitin ko itong Taylor's theorem para masulat yung equation 11.8. Balikan natin, ano yung equation 11.8? Equation 11.8 is our ansatz or our hula, our guess, or our template for our right-hand side dun sa ating gagawing method. Ano? Oops, nangyari? Ayan, ayaw niyang ma-highlight. But essentially, that's what we want to do, right? So gusto nating mahanap si A1, A2, lambda 2, at saka alpha 2, at saka si delta 2 para si phi ay maging approximation doon sa right-hand side ng Taylor's method of order 2, okay, T2. Alright? Now, ang gagawin ko, tingnan niyo itong second term na to. Sana mabura ko sila. Yan. Tingnan niyo itong second term na to. Itong second term na to, itong f of t plus alpha 2, y plus delta 2, f of ty, pwede kong i-expand itong buong second term na to, itong f na to sa second term in terms of Taylor's theorem. Okay? Remember yung Taylor's theorem, ang left-hand side niya ay f plus delta t. So gagawin ko lang, si lambda 2, siya yung gagamitin kong delta t sa theorem 11.1. Tapos yung delta y ng theorem 11.1, gagamitin ko ay delta 2 times f of ty. Alright? So that I'll get an expansion for phi. So, balikan ko siya dito. So, here we go. Ginamit ko lang ito at saka ito, plug in sa Taylor's formula, I'll get this guy in simplified expression. Okay? Now, in equation 11.10, that the factor R1 in the last term represents the error. Kasi kung babalikan nyo dito sa theorem 11.1, ito yung second order term, alright, na hindi natin alam yung exactong function value because all we know that merong number c at saka number eta such that itong expansion na to ay eksaktong magbibigay sa atin ng f of t plus lambda t, comma y plus delta y. Okay, t plus delta t plus y plus lambda. Ulit, t plus delta t, comma y plus delta y. But nalilito ako ngayon sa delta at saka sa lambda. But anyway, yeah. So this is the error term, okay? And if you look at that, ito yung itsura ng error term na yun. And it is of second order. Kasi lahat ng derivatives na involved dito sa error term ay puro second order. So this satisfies, or this sort of guarantee, ang tawag doon, parang na-realize natin yung promise natin kanina na gusto kong magkaroon ng order 2 approximation dun sa right-hand side ng Taylor's expansion, because if we will be successful to equate 11.10, kung etong first three terms ng equation 11.10 ay magagawa kong equal dun sa right-hand side ng Taylor's formula, then we're good because the error, which is A2 times R1, will be an order 2 approximation ng right-hand side ng Taylor. So our goal now is compare itong first three term na ibinox ko rito to the right-hand side of Taylor's formula of order 2. Para makita natin ano dapat yung value ni A1, ni A2, ni alpha 2 at saka ni delta 2. Because if that's the case, again, these three terms will be order 2 approximation para sa right-hand side ng Taylor's formula of order 2. All right? Is the process making sense? Sound ba yung plan natin? Kahit nangangapa ako sa PDF annotation. Okay, thank you. So now, ang gagawin ko, alright, ay kakopy-paste ko pala siya dapat. Paano ko ba siya makakopy-paste? Hold on. Hindi ko magawa yung magic ko na ano eh. Na i-encircle ko lang tapos madadrag ko yung mga pinagtatype ko. So balikan na lang natin. So si 11.8, siya yung equation, sorry, hindi pala 11.8. Nasaan yung right-hand side ng Taylor's? Okay. Ito pala yung right-hand side ng Taylor. 11.9. Okay. So in 11.9, ang coefficient ng function f evaluated at ti, comma wi ay equal kay 1. 1 yung coefficient niya. Tingnan natin dun sa Taylor's expansion. Ang coefficient ng f of t ay si a1 plus a2. So we must force the issue that a1 plus a2 must be equal to 1. And that's how we got this equation. All right? Tapos balikan natin. Dito sa Taylor's expansion natin, ang coefficient ng partial ni f with respect to t ay equal kay kay a2 alpha 2. Alright? So ito yung coefficient ng partial ni f with respect to t. So tingnan natin siya rito. So yung Taylor's expression natin, okay, there you go. Ang coefficient dito ng partial ni f with respect to t ay h over 2. So whatever coefficient of partial of f with respect to t in our Taylor series expansion of our function phi should be equal to h over 2. Balikan ko siya sa baba. Okay? Ang coefficient niya ay alpha 2 delta 2. Tama ba? Error pala yan, sorry. Ang coefficient ni partial ni f with respect to t ay alpha 2 a2. So that means alpha 2 a2 must be equal to h over 2. And then that's the same thing that's going to happen to the last term. The last term has is the coefficient of, I guess there's a typo here. Dapat ito ay df dy. Sorry guys. df dy. So ang coefficient dapat ni f ni partial ni f with respect to y ay si a2 delta 2. If we look at our expansion, if we look at the right-hand side of T2, ng Taylor series expansion, coefficient ni partial ni f with respect to y ay equal kay h over 2 times f. And then may times f din pala yung sa babae. So magiging equal din siya kay h over 2. So basically, I'm matching coefficients here. And that will give me the third condition, that a2 delta 2 should be equal to h over 2, right? So that means if I'll use these two equations, these last two equations, I'll get this relation. Kasi alpha 2 delta 2 ay dapat parehas equal kay h over 2a2. All right? Now, equation 11.1 basically gives us what are the conditions for a1, a2, alpha 2, and delta 2 para sa Runge-Kutta method of order 2. Kasi siya ay order 2 approximation sa Taylor's method of order 2. And you will see na kapag pinlogin ko itong mga value na to, wala ng computation ng partial derivatives or total derivatives. And that is nice because this method is of order 2. Kasi order 2 approximation nga siya ng isang order 2 method. Alright? Now, another thing about equation 11.11 is that it's telling us that there are infinitely many possible Runge-Kutta methods. All right? So bahala kayong pumili kasi wala tong unique solution eh. There would be an infinity of solutions for 11.11. So you could pick your favorite, say A1. Favorite number nyo, gamitin yung A1. Tapos, syempre, mako-compute mo si A2 as 1 minus A1. And then once you get A2, you could find the values of alpha 2 and delta 2. So it's up to you really to choose what those constants are. Yan tuloy, nagkaroon ako ng idea ng pwedeng ipa-problem set, kasi pwedeng iba-iba kayo pala ng Runge-Kutta method. Pwede kayong mag-imbento. Halimbawa, birthday niyo yung gamitin niyo sa A1, tapos birthday ni crush yung alpha 2, so pwedeng ganun yung gawin nyo sa problem set. Alright, so kaya lang it would be a nightmare for me to grade all of your works, alright? But I think that's fine. It's nice to play with this. Pero ang pinaka-common na mga ginagamit na Runge-Kutta methods ay modified Euler, the Rk, at saka the Optimal Rk2 methods. Pero before presenting those three variants of Runge-Kutta of order 2, tawagin natin yung Runge-Kutta of order 2 as Rk2. Usually ginagawa natin ng 2 stages para medyo organized yung pagkaka-compute kasi ang daming parentheses kasi ina-update natin. Remember, we have a sort of a corrector term here or an updating term, t sub I plus whatever the additional step size alpha 2 is, tas ito ay y plus delta 2 f of ty. Just to have a nicer implementation, una natin kino-compute ito, yung w tilde. Tapos masasabi nyo, si w tilde mukhang kamukha yan ng Euler's method. Kasi ito yung nakukuha nating approximate on the ith time step using Euler's method of step size delta 2. Alright? Tapos, kung babalikan nyo yung pinaka-format natin sa Runge-Kutta methods, alright? So ito ang naka-plug in dun sa isang function evaluation. So para lang maging organized yung computations, kaya gagawin natin siya in 2 stages. So first, you implement Euler's method, pero per time step to. So if you're on time step t sub I, kukomputin mo muna si w tilde. Para nag-Euler ka lang sa isang particular time value with step size delta over 2. Then whatever your answer is, siya yung gagamitin natin as one of the ingredients for the estimate for the function value at the next time step, right? So you'll just have wi, yung previous estimate galing sa previous time step, h times this guy, plus a2, then f evaluated at ti plus alpha 2, comma, yung w tilde na nakuha nyo kanina. So mas maganda tong expression na to kaysa dun sa napaka-messy na expression kanina. Okay? So ganito natin siya i-implement. And then as I promised, I'll show you 3 of the more popular variants of Rk2. Yung una yung modified Euler. So modified Euler, ang A1 ay 0. Pero remember, A1 plus A2 is equal to 1. So that forces us to have A2 equal to 1. Tapos, alam natin ang alpha 2 at saka ang delta 2 ay dapat parehas equal kay h over 2a. But a2 is equal to 1, so we'll have h over 2 to both values. Okay? So yan yung modified Euler's method na isang Rk2 method. Okay? So yung first stage, nag-Euler's method nga tayo ng step size ay delta 2 lamang. Right? Tapos kasi ina-update ko dito yung y value kasi siya yung ipa-plug in ko dun sa main formula. Naging dalawang terms na lang yung para kay w sub I plus 1 because remember, a1 is equal to 0, so the second term vanishes, so magkakaroon lang tayo netong dalawang terms na to. And the second term should look familiar because the second term is actually the midpoint rule sa integration. Okay? Kaya siguro naging sikat ito kasi kamukha ito ng midpoint rule sa integration. So that's the modified Euler's method. Tapos, yung isa pang usual na gamit ay si Unge method. Si Unge method naman, si A1 at saka si A2 was chosen to be both equal to 1/2, which is fine because the only condition we have for them is that A1 plus A2 should be equal to 1. And then alpha 2 delta 2 should be equal to what? H over 2A1 or A2. So dahil siya H over 2 times A2 it will simplify to h. And then you plug it into our ansatz. Okay? So pag pinlogin mo siya kanina, ganun pa rin. First stage, Euler's method. Ang step size ay delta 2. But delta 2 is equal to h. So this is essentially Euler's method on the ith time step. But you don't end here. Hindi siya yung talagang estimate natin kasi gagamitin ko siyang input dun sa second stage. Yung second stage pa yung nag-compute ng bagong approximate dun, ng approximate dun sa bagong time step. All right? And then you can just do the algebra. You'll be able to show that ganito yung magiging itsura ng W sub I plus 1. Okay? And this should look familiar because this is our good old familiar trapezoidal rule. Okay? And then the last method is the optimal Rk2 method. Okay? Ang choices naman dito ang A1 ay 1/4. Napo-force tayo ng A2 ay 3/4. Then, using the formula for alpha 2 and delta 2, we'll get the value 2h over 3 for both of them. Okay? And then we implement it in the two-stage formula or two-stage template na pinakita ko kanina. Ito yung final formula ng optimal Rk2 method. Alright? Now, tinawag siyang optimal Rk2 method kasi yung parameters na to, yung A1 equals 1/4, ang magbibigay ng pinakamaliit na numerical coefficient dun sa truncation error. However, discussion of the truncation error here will involve a lot of topics, so i-skip ko na siya. So gusto ko lang sa inyong ipakita yung actual method itself and basically how it is derived. Okay? So, questions? So, kaya nyo na bang inventohan? Halimbawa, Charles's Rk2 method o Michael's Rk2 method. Ano? So, kasi kayo lang naman pipili ng A1, A2, ng A1. Actually, A1 lang. Ano? Kasi pag alam mo na si A, pili ka na ng A1, mag-follow si A2. Tapos mula kay A2, mako-compute mo si alpha 2 at saka si delta 2. Alright? Everything's making sense? Questions? Okay ba yung reception or napuputol-putol ako? Alright, so okay, good. Thank you guys. So ngayon implement natin siya. Siguro pakita ko ng mabilis yung aking MATLAB code. Tapos pagalingan na lang mag-screenshot. Hold on. Kailangan ko palang stop share. Para lang magkaroon kayo ng idea paano magsulat ng isang ng isang simpleng Rk2 method program, ano? Kasi hindi siya ganoon ka-komplikado. Hindi mo siya kailangang i-program ng hiwa-hiwalay sa bawat isang method, all right? So hold on. Can you now see my MATLAB screen? Okay, good. All right, RK4 na pala to. Ito yung RK2. Ito yung sinulat kong generic program para sa RK2. Kailangan lang natin dito ay h equals 0. I-declare si h, ano yung boundary ng intervals kung saan tayo merong IVP. Tapos, ito yung time discretization. Hinahati ko na yung interval AB into a number of discretization points. Tapos, ito yung initial condition. Tapos, naglagay ako dito ng counter. Tatanungin ko si user, anong klaseng Rk2 ang gusto mo? Modified Euler? And when the user inputs method equals modified Euler, ito i-declare ko, ito yung parameters niyan. Ang A1 niya ay 0, ang A2 ay 1, ang alpha 2 ay h over 2, ang delta 2 ay equal lagi sa alpha 2. Right? Now, if the user will just replace mod Euler by yun, okay? So ito naman, dito siya papasok. Kapag ang method ay yun, ito yung values ng parameters. Okay? Tapos kapag ang method naman ay optimal Rk2 o opt Rk2 ang in-input ni user, ito yung coefficients. If you write your program this way, it's easy to add additional variants. Kung gusto mo, halimbawa, Ezekiel's method. So, lagay ka lang dyan, else if, strcomp, method, quotes, Ezekiel's method. Tapos, ibigay mo yung A1, A2, alpha 2, at saka delta 2 na gusto mo. Actually, dapat palang ginawa ko. Yung formula na kay A2 ang nilagay ko dito na 1 minus A1, Tapos ang alpha 2, delta 2, ginanong ko na lang yung formula. But that's fine. And then in the method, in the implementation phase, pupunta na tayo dun sa for loop, right? Ito yung for loop na nagko-compute ng estimate sa bawat time step, starting from the second time value. Kasi yung first time value, siya lang naman yung ating initial condition, okay? Now, line 28 implements the first stage. Ito yung implementation ng Euler's method para makuha yung pang-update natin doon sa function value dun sa second stage. And it is basically Euler's method done with h equals delta 2. Okay? Tapos pag na-compute na yan ni code for a particular time step, t sub I, t sub I, papakompute ko na ngayon sa line 29 ano yung approximate ko sa susunod na time step, yung w of I plus 1. Okay? So it's gonna be this formula nanggaling dun sa module wi plus h times a1 plus f of ti wi plus h times a2 times f of ti plus updated yung time value. We used the update alpha 2, and then the y value is already updated because that is computed in the previous stage. Tapos yun na yun. Yun na yung Rk2 methods. Ano? Then, pinakompute ko lang yung relative error and then the average errors. Never mind this line. Ginamit ko lang siya kagabi na naglalaro ako. Alright. Tapos yung function sa ilalim. It's nice to put your function f as a standalone function or as a function at the end of the script para pagkapapalitan ko yung function f, hindi na ako magta-type dito sa line 29 or whenever I see or I need a function evaluation. So you see here, I write f of t sub I, w sub I because I define the function f dun sa ilalim. So si function f of two variables t and w, define siya this way. So ito yung sa MATLAB syntax. Function f equals f of tw. Paano kinocompute si capital F na magbibigay sa akin ng ftw? Siya ay 1 plus w over t. Ito yung right-hand side nung IVP na sinusolve natin. Tapos ang kagandahan dito ay, pag na-declare ko to dun sa dulo ng script, dun sa taas, okay, dun sa buong main program, pwede ko na lang gamitin or tawagin si f of tw. When I call f of, I give two numbers inside of f, magdadirect si MATLAB, pupunta siya dito sa function defining the function little f. Okay? Para hindi ako edit ng edit dito sa taas kasi ilang beses ko gagamitin si f. So para isa lamang yung papalitan ko. Pag nabago yung right-hand side nung IVP, halimbawa naging t over w para dun sa isang example, i-uncomment ko lang tong line 49 tapos i-comment ko si line 50 para updated na yung function. Alright? So para mas madali siyang gawin. Okay? So I hope ganito kayo nagpo-program para pwede niyo siyang magamit sa problem set or whatever. Pag may pinagawa akong bago or lab exer, hindi niyo kailangan sumulat o mag-edit masyado ng code. Right? So let me go back to the module to show you the results ng calculations. Yes, CK, you have a question?
Pwede po sir, pa-scroll horizontally nung po sa line 32 kasi hindi ko po na-screenshot.
Sabi na nga ba, may nag-i-screenshot eh. Hold on. So lilipat uli ako na... Nakakapanibago pag wala ka sa usual setup mo, no? MATLAB, ay. Share, tapos window, tapos MATLAB. Okay, there you go. Line CK 32?
32 po.
Sabagay, printing lang naman to, no? Print F, eto.
Yun lang pala.
Alright. Okay, so okay na CK.
Sir, salamat po.
Right, you're welcome. Balik ako sa natin, sa PDF. Hirap ng isang device pala ginagamit. Or hindi lang ako sanay. Okay, now I'm back to the PDF. Pero gusto ko nakikita yung mga avatars nyo. So, second screen, punta ka. Okay, there you go. Okay, Now, I implemented the 3 methods to our favorite IVP. Ito yung pinagpa-practicean natin nun pa. But now, gagamitin natin yung Runge Kutta methods of order 2, yung tatlong variants, with the step size 0.5. So nagde-declare pa rin tayo ng step size dito kasi sila yung nagsasabi sa mga points natin kukumputin yung approximate dun sa solution x. Tapos ang function f natin dito ay 1 plus x over t. Kaya nakita nyo dun sa program ko, ang function f ko ay 1 plus w over t. Alright? Now, ito yung resulta ng pag-implement. So, try to recreate this using your own code. Okay? So, pag ginamit mo si modified Euler, ang relative error, ang L2 relative error ay 0.37%, which is very good, right? Actually, mas mababa pa yata ito dun sa Taylor's method kanina, na ginawa natin nung isang araw. Okay? Now, the Hoyne method or the Yoon method, ganun din, maganda rin siya. A little bit larger yung relative error niya, but still fine. It's just a little over 1%. Tapos pag si Optimal Rk2 yung ginamit ko, the error is a little over 0.5%. Okay. Tapos pag kinumpare ko to, mukhang pinaka-accurate yung nakuha natin mula kay modified Euler's method. But I don't think there's a general result telling us which one of those 3 methods will perform best. So I think it depends on problem to problem. So, pero the promise is hindi magkakalayo-layo yung accuracy na makukuha natin. Kasi itong tatlong methods na to ay pare-parehas of order big O of h squared, yung promise na local truncation error. The GDRE or the GDE, the global discretization error, ay hindi tayo sure. Okay? Kasi hindi ko na siya isasama yung analysis ng GDE kasi marami na namang preliminary results na kailangan. Okay? But makikita nyo naman sila ay halos pare-parehas. Kasi syempre, paborito ko yung ang hirap kasing basahin ng table, so nag-graph ako dito. Pinlot ko yung solution, yung exact solution, together with the 3 curves that we obtained using the 3 methods. Tapos makikita nyo, halos nag-overlap na silang tatlo. Can I zoom in? Yan, kahit mag-zoom in ako dyan, halos, oops. Yan. Mahirap na makita, or alam natin na meron pa ring deviations, pero almost nag-overlap na silang tatlo. Okay? Now, kinumpare ko yung L2 relative error nila. Of course, eto na naman, sabihin nyo, nilalait ko na naman si Euler's method. Si Euler's method ay 6.88%. Okay? Pero tingnan nyo yung T2 ay 0.76%. But the Rk2 methods, even without computing the total derivatives, ang ganda ng approximation. All right? It's almost in the same level or order as the Taylor series of order 2. Okay? Pero sasabihin naman ni Euler, madaya kasi si Rk2, yung mga Rk2 methods ginamit na ako. All right? Remember the first stage of this Rk2 methods, gumamit ng Euler's method. So understandably, dapat maganda talaga yung approximate para na manggagaling din sa Rk2s. Kasi parang 2 stages yung nangyari. First stage na Euler, so 6.88% lang sana yung accuracy doon. Pero after the correction or the adjustment or the updating, napababa pa nila into around 1% or even less. Okay? And then, ano pa nga bang ginawa ko rito? Okay, so that's it for the Rk2 methods. Okay. Now, you can extend the derivation that we did today para sa higher Runge Kutta methods. Yun nga lang, ang hirap niya nang gawin by hand because you will need a longer expansion ala Theorem 11.1. Sa Theorem 11.1, kinat ko yung expansion into the first 2 terms. And look at how messy it is already, aside from the mess that I made over here. So, ang haba. So, imagine kung gusto kong i-derive yung Rk4, so the Runge Kutta method of order 4, kailangan ko yung expansion ng f of t plus lambda plus delta t comma y plus lambda y. Bakit puro lambda yung delta ko? Ulit. Yung expansion ni f of t plus delta t comma y plus delta y dapat ay hanggang doon sa fourth partial derivatives. But look at the pattern here. I need to calculate all order 4 derivatives. Eh, ang dami nun. Yung ano nga, yung meron na nga tayo kagad na tatlong partial derivatives. Tatlong second order partial derivatives. So kung 4 yan, so ibig sabihin meron kang apat na order 4 with respect to t to the fourth. Okay? Tapos magkakaroon ka pa ng iba't ibang combination. Dadami yung number of terms dito sa error term. But if you are patient enough, you can do that and then equate that and compare coefficients with Taylor's method of order 4. Okay, then you will be able to calculate higher Runge-Kutta methods. For instance, RK4, which is I think the most popular. Pero may RK45 pa nga eh. Pero yung RK4 siya yung isa sa mga pinaka-popular na Runge-Kutta methods. But we will not derive it kasi hindi ako pasensyoso masyado. So, kinopya ko sa book, ito yung Runge-Kutta method of order 4. Actually, there will also be infinitely many Runge-Kutta methods of order 4, pero ito yung classical na RK4. Okay? 2 stages pa rin. Actually, simplified na pala to. Hindi na to naka 2 stage. So, assign mo lang yung initial condition, tapos yung approximate para sa next time step ay equal dito. Okay. And I forgot what this guy. Tama nga ba? Tandaan nyo ba? Ito yung, kung hindi ako nagkakamali, ito yung Simpson's rule. Yung 1/6 times K1 plus 2K2 plus 2K3 plus K4. Kasi minimimic ng mga Runge-Kutta methods yung traditional Newton-Cotes quadrature rules. Newton-Cotes nga ba? Newton-Cotes nga ba tawag natin doon? I think so. Or the Newton quadrature rules. All right. Now, the KIs are given this way. Okay. So, si K1, parang ano lang, parang Euler's method lang, na wala lang yung W sabay sa unahan, pero medyo komplikado na yung K2, K3, and K4. And encoding equation 11.13 into a program is straightforward, so I hope you can do this. Tapos, i-try nyo i-recreate itong ginawa ko sa example 11.4. In-implement ko lang si RK4 dun sa same IVP na kinonsider natin kanina. And just looking at the table of values I obtained, makikita nyo kagad na ang laki ng improvement. Kasi yung relative errors ay hindi nga lumampas ng 1%. In fact, the L2 relative error is of order 10 to the minus 4, which is very much low. And then if we compare it to T4, medyo slightly better itong sa RK4. Sa RK4, ito yung relative error natin. If you remember sa T4, ang ating relative error ay 3.8 times 10 to the minus 4. Okay? And then since I love pictures, let me show you the graph of the solutions or the exact solution, the one from T4 and the one from RK4. And as expected, halos wala na akong makitang difference doon sa dalawang graphs. Alright? Nakita na natin ito sa T4. Almost nag-overlap na siya with the actual solution. And this guy is nothing different. Paano ko ito Okay, kailangan kong mag-manual scroll. Makita nyo ay yan. Medyo may mga sumisilip na greenish part dito. Pero yung green na part na yon ay nanggaling kasi nag-combine yung anong nag-combine? Tama ba? Red plus anong pinagko-combine para makuha ang green? Nakalimutan ko na primary colors ko. Kasi bakit nagka-green dyan? Wala namang green dun sa legend, gumamit kasi ako ng, tama ba? Red plus blue ay green. Magagalit yung teacher ko ng grade 2. But anyway, that's the reason why you get green shades here. Nag-overlap. Blue at yellow. Thank you, Michael. Yeah, that makes sense. Blue and yellow. So nag-overlap yung exact solution at saka yung RK4. So halos nandun na sila. Okay? So pero makita nyo almost identical na yung tatlong graphs. So the lesson here is that ang hirap kasing i-implement ni T4. Kailangan ko yung tatlong total derivatives ni function f. Okay? But at this particular point, hindi na. Kasi kay RK4, puro function evaluation lamang yung ginamit ko. Look at this, all right? puro evaluation lamang ni F, what happened? Ang naganap para ma-compute yung for approximation. Oh, ano nangyari sa PDF ko? Wala na rin ba kayo nakikita sa PDF ko? Alright, sige. I-restart ko yung aking PDF. Last na, picture na lang ng relative error because really I love pictures kasi kaysa magbigay ako ng mahabang table, ang isang picture, ang laki na ng maibibigay niya sa atin na insights. Ano? So, nangyayari. Close all windows. Ayaw mag-close ng Adobe ko. So, hold on. Module 11, up. Susunod kasi ay para mas makita ko yung relative error. Kasi doon sa kanina, almost nag-overlap na yung tatlo. Hindi ko ma-visualize na si RK4 ay mas magandang approximation kesa kay RK4, ano? Sorry, kesa kay T4. So, pinlot ko yung relative errors naman. So, hold on. Binuksan ko siya sa edge. Sana hindi ito mag-hang. Okay, there you go. So, share ko na to. Last na to, guys. There you go. Okay. So, kita nyo dito na, kaya lang, pwede ako mag-highlight. Yes, there you go. Sana mas madali mag-draw dito. Makikita nyo dito yung relative error. Oh, mas smooth mag-graph sa mag-annotate sa edge. Alright? So itong blue, ito yung relative error at every point kay T4. Tapos makikita niyo yung red siya naman yung para kay RK4. And you see that ang laki nung difference, yung relative difference between the two. Nagkaroon talaga ng significant drop doon sa relative error, right? It would have been nice to investigate why this happens. Because this is a little bit counterintuitive because we said yung RK4 ay isa lamang order, isa lang good approximation dun sa right-hand side ni T4. And yet, why did RK4 give a better approximation than T4? Right? I don't have the luxury of time to discuss the detailed analysis of RK4, but yeah, you can explore it in your project. So if you want a more theoretical final project, then you can look into it. Okay. So, but I guess that's all that I want to say for this session. Okay. Now, ang idea rito ay on next meeting, we will look at multi-steps method. Etong mga tiningnan natin, Euler's, Taylor's, at saka Runge Kutta methods, lahat sila ay one-step method. Ibig sabihin, para makuha natin si W sub I plus 1, kailangan ko lamang yung value ni W sub I. Now, we can use other methods na magre-require ng mas maraming previous estimates or estimates galing sa previous time steps, right? So, pwedeng para makompute si W sub I plus 1, gamitin natin si W sub I at saka si W sub I minus 1. Okay? And that's what we will look at next meeting. Okay? And I guess that's it. Do you guys have questions? Yes, CK?
Sir, regarding po sa problem set,
Uh-huh.
may hint po ba sir para sa para sa values nung matrices? Like kung malalaki po ba yung exponents or yung
Nakalimutan ko
error ay
siyang
maliit or malaki?
Yeah. Nakalimutan ko siyang gawin. Maybe you can talk among yourselves, pero siguro, chat mo ako siguro CK by tomorrow noon pagka hindi ako nag-update. Tapos mag-i-email blast na lang ako sa inyo. Okay lang ba yun? So, i-ano nyo muna. I-hold in abeyance nyo muna yung inyong problem set 2.2 kung hindi pa kayo sure. Ano? So, mag-integrate lang naman doon. No? Actually, hindi naman mag-integrate. Kukomputin ko lang, gagamitin ko lang yung formula, no? Pero ang tamad ko kasi hindi ko pa rin siya ginagawa. Pero I'll try. Marami lang akong meetings after this and then may conference ako tomorrow. But I'll do my best to send an email blast siguro by tomorrow noon. Okay? Pagka nakalimutan ko ulit, paalala na lang CK. Alright?
Sige po sir, salamat po.
All right, thank you then. Okay, so other questions? All right, so wala na. Oh, nakita niyo na hopefully yung lab vector again, ang deal natin in-extend ko man yung deadline ng problem set. I-keep natin yung deadline ng lab vector to be on Monday, all right? Pero yung lab vector binigay ko kahapon, it's an epidemic model, ano? Ang kailangan niyo lang naman gamitin ay Euler at saka uh, Taylor method nga ba of order 2 yung pinagawa ko ron. So I hope you guys can work on it, okay? Now, medyo komplikado nga lang siguro yung Taylor's method of order 2 kasi medyo mas komplikado yung right-hand side ng ODE na binigay ko. Alright? But anyway, if you're having troubles about it, so pwede nyo akong email over the weekend or if you want, you can wait until Monday para sa lab sessions. Okay? Para magkaroon ng clarifications about that final or about that lab excerpt. Okay? So, sorry, nakita ko nag-chat yata si Charles. Kaya lang di siya nag-appear sa Teams ko. Tingnan ko siya sa... okay. Nagjo-joke na naman si Charles. Euler doesn't have any questions po. Wala na. Busy kasi siya kasi ginagamit pa siya ni Runge Kutta sa first stage ng Runge Kutta. Okay. So, anyway, that's it for today, guys. Enjoy the weekend. And then let's meet again on D2L sa Monday. And then the rest sa Wednesday. But until then, guys, keep safe. Bye-bye.